Welcome to this week's Flipped Classroom. We're going to start the year talking about geometry definitions. Okay, so we're going to start with a couple of assumptions here. The first is that we are working in 3D Euclidean space. Okay, so there are a lot of spaces out there, but we're going to be working with the flat plane geometry. The other thing is that we're going to leave some things undefined, and we'll talk about why we're going to do that in class. First definition, let's start with the zero dimension. A point is a geometric object or shape that has no length, width, or depth. We model points with a dot and name them with a single capital letter, usually from the beginning of the alphabet. And here we have a diagram showing as an example. We see that the red dot is in the top left corner here, and it's signified with the letter A. Moving up a dimension, we have a line. Is a geometric object or shape with no width or depth, but infinite length in two directions. We model lines with a straight edge with two arrows on its ends and name it with the 2 points on the line, such as AB. Or sometimes we use a single lowercase letter, usually in the middle of the alphabet. I'm going to try to stay away from these. Naming it with 2 points, we will find, makes a lot more sense. So I will more often than not use the symbol AB. In the first dimension, we have a ray, a geometric shape or object with no width or depth and infinite length, but only in one direction this time. So contrast that with a line that has two directions. A ray only has one. We use similar notation for this, but an important thing to note here is that you must start your naming with the end point. So for example, I could not name this ray that you see here BA. It has to be AB. Now, if there was another point on the ray, let's say C, we could name it AC, but we could not name it CB or BC. One of the letters has to be the starting point. Last shape in the first dimension is the segment, or sometimes the line segment. It is a shape with no width or depth, just like the other two, but has finite length. Now, finite, again, means it ends. We model the segments, again, with two endpoints, and we name it with its endpoints. So again, if there was another segment on here, another point on this segment, let's call it C, we could not name that same segment AC. It has to be AB, the starting and the end points. Now, of course, we could name it BA because we don't know the orientation, where it starts or where it ends. Up into the two dimension, we have a plane. This is a geometric object with infinite length and width in all directions, but no depth. We model planes with a flat surface and name it with three non-collinear, and I notice I have that set underlined, but we'll define it in a second. You need three non-collinear points. Very rarely, I don't like to do this because it's a little confusing. You could name it with a single capital letter. So, if we look at this diagram here, we have a number of planes. We could name that plane P, that is the flat plane going across the very lighter gray plane. That's okay. I would prefer if you use something like CAE or ACE. Also, you have the other plane that's vertical, the plane R. Again, R is not a point, it is just a letter signifying the plane. It's in cursive in this diagram. An acceptable way to name it could be GAF, but notice BDA is not an acceptable way to name either of those two planes because those are of the same line, which means they are collinear. And if we said, okay, plane BDA, you don't know which one I'm talking about. Am I talking about plane P or plane R, or maybe even a different plane? So we have to make sure that these 3 points that we pick to name the plane are not in a straight line. Angle is a two-dimensional shape. We have two rays with a common starting point. It's kind of interesting naming angles with by using the idea of rays. A lot of students get confused by that, but if you take out a piece of paper and you draw an angle, really what you're doing is you're drawing two rays. We model angles with two rays and name it with 3 points, a point from each ray, such as what we see here, and the vertex, again, another underlined word here, which is the common endpoint, the point that the two rays have in common in the middle. So the proper way to name this angle is AVB or BVA, but ABV is not an acceptable one, and neither is CVBA would not be an acceptable one. Another alternative way to naming it is if there's no ambiguity, just the vertex point works. So in this case, we don't have any ambiguity, which means it couldn't stand for something else. So if I said angle V, you knew what I was talking about. But let's look at this diagram right here. If I said angle C, you knew what I was talking about. It was the same as angle 3. But if I said angle B, you wouldn't know which one I'm referring to. Am I referring to 1? Am I referring to 2? Am I referring to the combination of 1 and 2? That's what it means to be ambiguous. So when you're naming angles, make sure the safest thing you can do is to just grab 3 points. So if I said CBD, you know which one that is. You can trace along that with your finger. You can put your finger at C, trace it to B, and then trace from B to D. And you'll know that I'm talking about angle 2. These are important things to make distinctions for, because again, sometimes it doesn't matter, but other times it does matter. And if you're going through a proof and you just give an ambiguous angle, it's not going to be a good proof. Move through relations, okay? An intersection, this is something that's kind of hard for students to describe. It's usually where things cross is one way to think about it. But technically speaking, it is shared points. It's the points that you have in common of 2 or more geometric objects. So if you had 2 lines, M and L, their intersection is a single point, C. That's the points that they have in common. C falls on both M and L. Next, if you have a line and a plane intersecting, there's a couple of different possibilities. First, you could have B and the plane. B is the line. The plane does not have a name in this diagram. But if I just refer to the plane, hopefully you know what I mean. Those two have 1 point in common. But if I said the plane and A, those have the entire line in common. And in fact, you could also intersect 2 planes. If we look at the intersection of planes A and plane C, we notice that it's a line X. Likewise, plane C and plane B have the intersection of line Y. Collinear is the next definition. Again, we talked about it before. Coplanar kind of goes in the same idea here. Basically what that means is they either fall on the same line for collinear or the same plane as coplanar. So here's an important distinction though. If I said pick out 2 collinear points, you could obviously say A and B, because you can see the line that's drawn through. Although, even though you can't see the line, you have to also see that A and C are also collinear, because you can imagine drawing a line between A and C. So what might be an example of a set of points that aren't collinear? Well, A, D, and E are not going to be collinear because there's no way for you to construct a line between A, D, and E. Okay, so you have to remember that. I put an important note on the screen right here. Just because the object isn't drawn in the figure doesn't make them non-collinear or non-coplanar. One example perhaps of non-coplanar points, maybe we have C, A, and E and point H. Those 4 points do not fall in the same plane. C, A, and E do. Those are coplanar points, but H goes above it, and there is no way to construct a plane that goes through all 4 of those points. Talking about parallel. So parallel lines are coplanar lines that do not intersect, and you do need that extra first word there. Sometimes when I ask what are parallel lines, students say, oh, they're lines that don't intersect. But in fact, you could have a set of skew lines. These are non-coplanar lines. So we imagine if you had an edge of a wall, let's say, where two walls intersect, you have a line there, and maybe on the other side of the room you have where the wall hits the ground. Those two lines, one's vertical and one's horizontal, they don't intersect, but they aren't parallel either. Those are actually skew. And finally, parallel planes are kind of what we imagine them to be. They're just planes that don't intersect. So let's do a couple of examples here. So parallel lines. If you look at the two edges of the plane, even though planes don't technically end, but in our diagram, the right and the left edges of plane P are going to be parallel. Likewise, we could probably say the up and down of the two, excuse me, left and right of the dark gray plane R, those guys are going to be parallel. So what would be an example of ones that are going to be skew? Well, imagine the left edge of plane R, the left edge, you see that? Compare that to the right edge of plane P. Those two lines are definitely not parallel. They don't go in the same direction, but they are not going to intersect either, so those are skew. I just want to reemphasize something here. This diagram is just that. It's just a model. It isn't a perfect representation of two planes. Two planes, or planes in general, do not have edges. So we're just looking at a piece of planes in this diagram. Last set of relations, we have congruent means the same size and shape, and we're going to kind of leave these two things undefined, but the best way I can describe congruency is this following statement here. One shape can be mapped to another using only translations, rotations, and reflections. So if you have two shapes, and if you change one of them by just shifting it around and flipping it around, and it matches up perfectly with the other shape, then they're congruent. Now that's not a good proof, but it's a best way to explain what congruency means. It's the equality of geometry. Finally, we got three more, I believe, here, statements to consider. We've got a postulate, or sometimes I will say axiom. This is a mathematical statement that is accepted to be true without any proof. Again, we'll talk about this in class, why we need those things. Something you may have heard before is a theorem, a mathematical statement that is proven using postulates and definitions. So if you have a theorem that states in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides, that is a theorem that must be proven. It's a very famous theorem. Next is a corollary. This is a theorem technically because it does involve a little bit of a proof, but you don't need too much of a justification. It just follows from another theorem very quickly. So usually it's a couple of lines to justify, but it really follows from one big proof. So where I received the pictures, and these are actually some pretty good websites to check out. Some of them are relevant to the class, some are not, but I want to thank all those who helped in creating this flipped classroom.